assignments, doubts, exams. We have got you back. EduPlanner make every chapter easy to understand. Stay tuned, learn more, grow with us.
So this problem starts off with taking an example from earlier in the chapter where there's a meter stick that is suspended at point O and is oscillating, where C is the center and P is the point on the pendulum that marks the center of oscillation. And so our H is the distance between O and C. This problem goes on to say, okay, let's say we inverted the meter stick, inverted the pendulum, so that it was actually suspended from point P rather than point O, making our H is no longer the distance between O and C, but now the distance between P and C. And so that is going to make a big difference for us because our H is now going to be equal to 2/3 the length minus 1/2 the length, which gives us an H of 1/6 the length of our original pendulum. We can now use this to calculate our moment of inertia, and using the parallel axis theorem, we can change this to find our inertia so that we know inertia equals 1/12 of our mass times the length squared plus the mass times h squared. And so now we can substitute those values in so that we have inertia equals 1/12 our mass times length squared plus our mass times 1/6 L squared. And we get that comes out to be 1/9 mass times length squared. Okay, now substituting our inertia into our period formula, we get that period equals 2 pi times the square root of our inertia divided by our mass times gravity times our height, which when we put in our values, we get 2 pi times the square root of 1/9 our mass times length squared divided by mass times gravity times 1/6 our length, okay, which we can simplify. The mass will divide out, and we end up getting that our period is equal to 2 pi times the square root of 2L over 3G. Okay, and so finally, since we know it's a meter stick, we can actually substitute in for our length, and we know what gravity is. So we can actually calculate our period, which is 2 pi times the square root of 2 times 1 meter divided by 3 times 9.8 meters per second squared, which gives us a period of 1.64 seconds. And that is our total, that is the period of the inverted pendulum. Now in the book, the original pendulum, where it was hanging from point O, also had a period of 1.64 seconds. So even though we've inverted it, the period is the same.